So it's the so we are considering a communication class so that I and J communicate with each other. Right? And the first part, I said mistake. It's a stronger or large number for multi-chain. So let's see how do we deal with the proof. So it's basically it's saying that given the initial state is I, and that the fraction of chance to visit state J as t goes to infinity is equal to 1 over the mean return time for state J. So this is the mean return time for state J. Okay, so let's see how to prove it. Alright, so we first consider a case that I and J are transient. That means that we are considering a transient communication class. Alright, and so we already know that if J is transient, and so that this probability is 0 because for a transient state you are unable to visit the state for many times. Right? So condition on the initial state to be equal to I, then that the total number of visits to state J is finite to be 1. Alright, so that for all t, alright, for all t in R, the NJT has an upper bound here. Okay, we have an upper bound. And this upper bound, as we say, is finite to be 1. So that as t goes to infinity, the fraction of time to visit J will be upper bounded by this constant divided by t. But this goes to 0 as t goes to infinity. Okay. And of course that so this is 1 over mu jj. So of course, so it's 0. And as we know that this is a positive number, so the lower bound for this ratio is also 0. So you can see that the limit is actually 0. Okay. Any questions? Alright, so now the first is true. Sorry. Okay, so now for trending cases, the first is true. Right, this goes to 0. Okay, because mu jj is infinity, so this is 0. Okay, and so now we follow. In the following, we will prove the second, and third, and the fourth item for transient states. Right. So now this has an upper bound. All right. The part sum here has an upper bound. All right, and this upper bound is finite, as we know that for transient state, we prove that this is finite. Okay. So that this ratio, as n goes to infinity, is upper bounded by this one. So this is 0, true. Right. So this is also true. Okay. And we also know this goes to 0. Okay, goes to 0 because that this is series sum. This is finite. So for a convergent series sum, the terms here will goes to 0. So of course this is true. Right. So now so no matter the state is a periodic period, This is true. This is true for trending state. So we go to here. So no matter what is a periodic or periodic, it goes to 0.
periodic 可以画得出来，讲一下什么叫 periodic。
periodic, well, this is a period. You know. For example, if we have 3 states, so yeah. So this, of course, this is a periodic because that we take a look at 1. So see, 1 goes to 3, goes to 2, and goes to 1. So at least you have so you have P11 0 because P11 0 0, right? So it is, but it is, and the P114. So when we have P14, 3, 2, and this. So you can see because if you start from 1, you have to go back from 2, right? So this is always necessary, okay? But internal you have a loop here, right? So either you have 3 to 1 or you have 3 to 2, 3, 2, 2, 3, and 3, 2, right? So you have 3, 2, 2, 3, and 2. Okay, so you have 1, 2, 3 more, right? So this is 0. Okay. So you can see if the steps is order is 1, it is odd order or odd steps, then you have positive transition probability. So see that the state say Q of N such P 1. So you collect all the N here. And this is actually for here. This is 2n plus 1 for n. Actually, it's that. And also the GCD of Q is equal to 1 because the common divisors is 1. So it's a periodic. And the other cases is that it's very simple. So this one. So you can see the period is 3. Okay? Because it's 1, 2, 3, 1, 3, 2, 1, 3, 2, 1, 3, 2. So you see that this is the periodic and the period is 3. So that the theorem is true if we are considering transient states. Okay, so if I and J are in a transient communication class. So the next cases will be I and J are in the same recurrent class. Here it is. Okay, so now we consider the case that I and J are recurrent. But in theorem 4.2.5, for this particular case, we have so actually we have a renewal process to model the process of the Markov chain. So here, condition on the x0 equal to I, then that the successive time to visit state J. So T1J is the first visit time to state J. This is the second visit time to state J, etc. Okay, and so given the initial state here, this is successive visit time to state J. they form a delayed renewal process. Okay, and this is because that the first visit time from state I to state J has distribution which is different from the first return time. Means that the inter visit time of the state J. So this is a delay renewal process. Okay. And because that they are recurring, so we know that all these terms they are finals for V1. Okay. Now, and the first arrival time and the inter-arrival times, right, are lattice, and with the period d when the period d is equal to 1 when I and j are periodic states. But if I and j are periodic with period d, then d will be greater than 1. Just like in this case. Okay, in this case, the period is 1. In this case, the period is 3. So we do have period. Okay, so that these features of periodicity is important in the study of Markov chain. Okay, so now we know that. Alright, so condition on the initial state I, this is the interrupt time. And the expected interrupt time actually is this one. Alright, it is the mu jj, as we defined before. So, so the proof will be when we're applying the renewal process, the renewal theory for the delay renewal process, especially the position 3.5.1 we mentioned in the last chapter. Then, so basically, because this is just the renewal property. So, for example, the Stochastic large number for delay renewal process implies a condition on the new state is 1. This is true with V1. We already know. We already proved that before. Okay. Now, and So this is the number of total number of visits to state J up to 10 detail n, right? And so by the indicator we know here, and so this is actually this probability. Okay. Okay. So basically, actually we developed these equations before. So anyway, so by the elementary renewal theorem or delay renewal process, alright, so we know this one. Okay, this is the expected version. You know, the elementary renewal process theorem is just the expected version of the renewal theory. So this is actually this one, the expectation of NJ. Okay, NJ. It's just that's our mean function, right? Remember, remember that, and the MT, right? Limit equals infinity, right? It is the what is that? Is the interrupt time, the mean of interrupt time. Now, the time is just the integer time only. So this is just the mean function. You can see that, and so the t is just we just take the integral time, right? And so this is mu. So this is exactly the elementary renewal theorem we proved before. Okay, so this is the second part. Now, by the Blackwell theorem for the delay renewal process, so this is also in theorem 3.5.1. All right. So whose first arrival time and inter-arrival time are dated with period D. Okay. In this case, we know that this is always the given condition. The expected number of renewal at time ND, okay? Because it occurs periodically, so we just say the number of renewals at time ND is equal to D divided by NJJ. Okay. So the expected number of renewals at time ND, is the conditional expectation of the number of transitions into stage at time ND. Okay, so this is actually just an indicator only, because at a time either you have a visit to J or not. Okay, so this is indicators here, and so this is just the n times d steps in transition probability from state I to stage.
And is it always positive?
Well,
Because
you know, yeah, because that not necessarily for some initial multiple of D, but eventually will become positive. This is a property. Well, I think maybe there is some exercise. Why? For example, you see, in here, you know, I say it's odd, right? But the one is an odd number. But the probability, the transition probability in one step is 0. But starting from 3, this you have non-zero.
For the upper one,
But you're already 3, right?
yeah, so it is
6 always.
so it's always positive when you
Yeah, starting from that. In general, if you have a period D, right? But in some initial multiple of the period D, you may have a 0 transition probability, right? Maybe, but eventually, at some later time, okay, then you have the later consecutive multiple of D, you have positive transition probability. It is a property of multiple trends. Yeah. So, but this can be seen from this linear process, right? Because it goes to here, and this is a positive number. So you can see as n big enough, it will cross to the limit number. So this probability will be stable, will be non-positive. That's of course. Unless what? Unless this is infinite, it's possible. If we have no recurrent state, right?
If it is transient and it is 0.
Yeah, but for example, for no, even though it's recurrent, but if it's no recurrent, then mu JJ is infinite. No, because we define how is no recurrence if the expected time to return back to J is infinite. Okay. So it's possible to go to 0, but when it goes to but it goes to 0, but in finite number of finite number of multiple of D, then it is positive, but it just declines to 0, right? Asymptotically. Okay, so basically we prove the theorem. So the proof of the theorem seems very simple because we have developed the renewal theory in chapter 3. If we didn't develop the renewal theory in chapter 3, then the proof of the theorem would be much more involved. You know, right? Okay, so all right, so this is this theorem contains the fundamental linking behavior of the Markov chain. Any questions? Okay, so yeah.
Why do we call class properties? What does it mean?
Oh, class property means that if so, for example, I and J, they communicate with each other, so we say that they are in the same communicating class. then the same class. Alright. The class problem means that if, for example, when I is transient, then J must be transient. Okay. So in a class, the transiency is a class property because one state in the class has a property, then all the other states in the same class will have the same property. So transiency is a class property. Recurrence is also a class property. If I is a recurrent state, then J must be a recurrent state. And we can differentiate the recurrent class into non-recurrent and positive recurrent. So if I is positive recurrent, then J must be positive recurrent. On the other hand, if I is non-recurrent, then J must be also non-recurrent. Now, for the period, if I has period, for example, 3, then J must has period 3. Right. So periodicity is also a class property. And if I has period 1, means it's a periodic, then J is also a periodic. And so all the class property has to be proved. So actually we prove all the class property before. Other questions? Yeah. So this is so I want leave this as an exercise. Okay. I think you can use actually you can call help from this film. Okay. All right. Now, it is possible to make the Markov chain to be a stationary process, right? So here is the start. We call a distribution of state. It is called stationary if this is true. Okay. So that means that we know Pi. Pi is for example, if you take a stationary distribution as an initial distribution, then this is the distribution of the second state. Okay. Right. Or just take as a definition. So we say a distribution of state is called station if it satisfies this system linear equations. Right. So Pi and in vector form, that if we write a distribution as a discrete vector, right? So this is a vector, even though it is infinite dimensional, anyway, but just a column, a row vector here. So it's called a probability vector because that the components they are all non-negative and the sum of all the components is equal to 1. So such a vector is called a probability vector. And we write all the one-step training probability into a matrix here. So the first row it is the transition probability from state 0 to state I, right? 0, 0, 0, 1, etc. Okay, so we just the row sum is equal to 1. Okay, so the row sum P00 plus P01 plus P02, etc. Alright, is equal to 1. P10 plus P11 plus P12, etc. equal to 1. Okay, so they have the row sum of the matrix are equal to 1. Right. Alright, and so this system of linear equations can be written by this matrix equation. So the probability vector, the row vector, is equal to the same probability vector times the one-step changing probability matrix. Okay, so this is the so any probability vector satisfy this equation is called a stationary probability vector. Now, so if the initial state, so now we want to prove that if the initial state x0 is the stationary distribution, then the distribution of all state, right, at any time n greater than or equal to 1, what has the same distribution. So it's called stationary. So actually, from the marginal distribution point of view, that the Markov chain will have the same marginal distribution for all the time. And we can prove that by induction. For example, if n equal to 1, all right, so we want to know the distribution of x sub 1. Right, and by so this is the this is by the total probability theorem. Okay, this is total probability theorem, and this is the equation. So this is Pj, because we have initial distribution, which is just Pi, yeah, and this is the one-step training. And so this is Pi. So you see that the x1, the state at time 1, has the same distribution as the initial state. Right. So n equal to 1 is true. Now assume this is true for any n greater than or equal to 1. So we now consider the next the distribution of the next state at time n plus 1. Okay. Again, we use the total probability theorem again here, right? And this is by the induction step that the xn is the same distribution as the distribution here. Okay, and so this is Pj. Okay, and now we have Pji. Okay, and then we have Pi here. So by induction, we have shown that xn has the same distribution as x0. And furthermore, when we consider consecutive, the joint probability of the consecutive n plus 1 random variables in the Markov chain. Okay, so we want to know the distribution. Okay, so it's consecutive from m to m plus n. So we have n plus 1 random variables. All right, and so we just write down the joint distribution going to be here, and then by Bayesian rule and also the Markov property, right? By the Markov property here. So here this is x, and because our Markov chain is time homogeneous. Okay, our Markov chain is time homogeneous. All right, so this. I'm sorry. Yeah, the Markov chain is time homogeneous, so the training probability comes to this one. Okay, so m is 0, 1. Okay, so you have that. Okay, and because we just proved that the distribution of the Sm is equal to the distribution of x0, so we can shift it down. This is by stationarity here. Just proved. And then finally, combine together. This is here. So you see that the joint distribution is independent of the shift m. Okay, because this piece of information is just a shift from this piece of information. Okay, so indeed, we proved that the joint distribution is independent of the time. Okay, the time index here. So this is truly so that so when x0 is distributed with a stationary distribution here, then the Markov chain becomes to a stationary stochastic process. we defined before, a stationary stochastic process means that the joint distribution of the process is independent of the time shift. Okay? So that is called the stationary distribution, stationary stochastic process. Any questions? Okay, so now, if the initial state has stationary distribution, then we have to say, so now we want to find okay, so if we know that the distribution at the time n, right, is actually can be expressed by the n-step changing probabilities. Okay, so this is the n-step changing probabilities. But we already know that this is true, right? So basically, P is due to Pn. I think that we can prove that directly from the fact that because when P is stationary, so we already know that P is P, right? But again, P equal to P, so it's P squared. Okay, and this is P, okay, right? So by induction, we can multiply. So in general, P equal to Pn. Okay. And if the state space is finite, so here, how do we find the stationary probability vector? Actually, we are going to solve the eigen problem, right? Because that you see that P actually is a eigenvector for the one-step changing probability matrix. Okay. But in linear algebra, we express the eigen problem in here, right? Okay, so this is a matrix and X is the column vector. Right, so we solve the problem. And so, but in probability theory, we write the vector as the row vector. So actually we have E equal to P. And so this is 1. So the eigen value is 1. Right? So we are going to find that eigenvector corresponding to eigenvalue 1. And this eigenvector must be a probability vector. Okay? A probability means that all the component is non-negative. Okay? So it is equivalent to find the eigenvector whose components are all non-negative. Because after you find an eigenvector with non-negative component, you can normalize it to be a vector, a probability vector. Okay, by normalization. So, for example, if you have 2 and 3. Suppose you have that. Then you can divide it by 5. So of course, so this probability vector will satisfy the eigen problem. So the problem is that if the state space is finite, so the one-step changing probability matrix is finite. It's finite matrix. And And so you can just solve. You can solve T. Okay? You can solve the eigenproblem corresponding to eigenvalue, which is equal to 1.
But how do you know the P matrix has eigenvalue equals to 1?
Equal to 1?
How do you know that it has an eigenvalue equals to 1?
Yeah, because then we can prove that. Yeah. So actually, well, I would say I'm going to prove that in my linear algebra class in this semester. Anyway. Okay. You can find a proof in the literature, but if you would like me to give you a proof, just let me know. I will send you a note. Right? So, so this is true if P is finite dimension. Okay. And actually later on, we will have a proof. Actually, you will see. You will see that in some cases you don't have 1. Okay, you don't have 1. Why? If P is infinite dimension, if the state space is infinite, then you may not have a B vector. But you will see if P is finite dimension, if the state space is finite, then there exists at least 1. And in many cases, you have infinite many. Okay, and so I will give you a proof. So this is a topic of the rest of the chapter. I will give you an answer. All right. Okay, so now, so to give you a general answer for your question, we first consider a special case. So let's consider a Markov chain consists of a single communicating class, like this one or this one. So this Markov chain has 3 states, and the 3 states are in the same communicating class, right? And this is true. Right. So because in general, a Markov chain can have many different communicating classes. But if we only have consider a single communicating, it's called irreducible. Right? It's called irreducible. So now the theorem. An irreducible and a periodic Markov chain belongs to one of the following 2 cases. Either the states are all transient, or all recurrent, right? All this, because transiency and the recurrency are class properties. Right? So so either states are all transient or all recurrent. In this case, then the limiting behavior of the n-step chain will be from I to J. Because you see that I and J are in the same communicating class. Okay. So that the goes to 0, and there is no stationary distribution, right? For this case, alright. So there is no stationary distribution. The second case is all states are positive recurring, right? So that the limiting behavior of the n-step chain probability will go to 1 over mu J. And this is finite. Okay, this is finite and positive. Okay, so we define this as pi chain. And it's very interesting, from our integral, this is independent of R. Independent of R, okay? Just depend on J only. So all the states are positive recurrent, and the limiting value of the n-step chain probability is from state I to state A is constant, and this pi j is positive. And in this case, the pi j is a stationary distribution. So we prove the existence of a probability, a stationary distribution, okay? And we know how to compute it. And there is no other stationary distribution, so the stationary distribution is unique here. So this theorem answer just part of your question, right? Partially, I mean, but you will see gradually. You will see that the whole picture can be composed by using the theorem here. You will see that. Okay, so this is so for irreducible and a periodic market chain. Right, and we have this one. Okay, so we go to proof. First case, either the states are all transient or non-recurrent. Now we apply our limiting theorem. In theorem 4.6.1, we know that this limiting probability, right, is equal to 1 over mu jj. And for both cases, either transient or non-recurrent, this mean is the expected first return time is infinite. So 1 over mu is 0. And this is true. Whether the market chain is periodic or non-periodic. Okay, this is also always true. Now, so up to now we know the fact from the theorem 4.6.1. So if the market chain, if the market chain has a stationary distribution pi, right, means that suppose we have a stationary distribution like this one. Okay, then now. Okay, so we let n goes to infinity because this is true for all the n, right? So we just take the limit as n goes to infinity. Of course, this is constant, right? So there is no problem with that. And now just come up with this one, all right? And because everything are all positive, so we can exchange the limiting. This is also a limiting process. So the sum, the serial sum, and the limiting process can exchange order, right? So when we exchange the order, we have this one. And now, but we know the limiting behavior of the n-step changing probabilities goes to 0. So 0 times pi are all zeros. Okay, and this is a contradiction. Okay, so because we assume that we have a stationary distribution. To have a stationary distribution, we have to have this identity here. Okay, for all n greater than equal to 1. But with this one, and by applying the limiting behavior, we end up with a contradiction. So that means that the market chain has no stationary distribution. Okay, so for the case here, for an irreducible periodic or aperiodic market chain, which is transient or non-recurrent, then the market chain has not a stationary distribution. Okay, so the proof, actually the proof, we have a much more stronger result because this is true for irreducible aperiodic and irreducible periodic market chain. If the market chain is transient or non-recurrent. Okay, so we settle the case. So now, but if all states are positive recurrent, then we need that is aperiodic. Okay. So let's go to here. So all states are positive recurrent. Again, by the theorem, we have this one too, right? So because this is periodic, otherwise, if it's periodic, you have to see here. Go over here. If J is periodic, then we have this. But if it's periodic, we can't have that. We have to. We have only got the multiple integral, the multiple of D. So that we have that expression. Okay. Right, so all states are positive recurrent. Right, and because we already assumed the multiple changes are periodic, so we can apply theorems. The third item of theorem 4.3.1, so we have this one. Alright, and I made the proof because that the proof in the textbook, in the rest, right, is still good enough for me. So the proof in the textbook, text 2 step. First one, we prove the existence of a stationary distribution, okay, and by applying this limiting process. And we prove that every stationary distribution is indeed equal. Right? So I just leave the proof for you to look at the textbook. But before you read the proof in the textbook, I encourage you to study my lecture note first, okay? Because my theorem is much more general and better than the statement in the textbook. Okay, so actually from theorem 4.2.2, we have established a good result here that if the reducible Markov chain is transient or non-recurrent, no matter it is periodic or aperiodic, the Markov chain has no stationary distribution. Okay, and we have this one. So this is from the theorem 4.3.1. But the new result is here. There is no stationary distribution. But if the Markov chain is positive recurrent and it is aperiodic, then it has a unique stationary distribution. And the unique stationary distribution can be found out by this limiting process. Okay, so actually the pi j here consists of a stationary distribution. Okay, so the remark actually just stress the same thing I mentioned. So the first part is true for any invisible, periodic, transient, or non-recurrent check. Okay. Okay, so. And now the remark answer the part which has been left over is that if we have an irreducible and positive recurrent Markov chain, but it's periodic. Okay, so for an irreducible periodic positive Markov chain, then we still has a unique stationary distribution, and this stationary distribution is just 1 over mu. Okay, same here. So, so this is an exercise. So this remark just give us the whole picture already. Okay? So it's the same as here. Okay, the case, but it's not going from an linear process. Okay, because it's periodic. So for example, you see that you have if the Pn, say here, Pii always 0, right? Always 0, and P always 0. So the Pn has no value, but the P okay, plastic. Okay, and so that you don't have a convergent sequence. If you want to know the Pn, okay, you have no. For example, Pii, because it's something 0, 0, something 0, 0, something. So never converge. So the sequence here for periodic, this is a Mark chain. This sequence does not converge, okay, because it's oscillation. Okay, oscillation. Oscillation here. But the remark state that the same type I, but 10810EE still consists of a unique sectional distribution for irreducible periodic positive recurrent Markov chain. Okay, so let's take a short break for 5 minutes. Irreducible Markov chain means that this Markov chain consists of only one communication class. But the general case is that a Markov chain can consist more than one communication class. So we have to know the transitions among communication classes. We have to know that. Alright, so now we consider a recurrent class. So R, we use R to denote that it is a recurrent class in a Markov chain. Alright? And then we pick up a state I in the recurrent class. And a state J not in this class. But we don't know what is the property of state J. J can be transient or can be recurrent. Anyway, right? So the point is that I and J are in different communication classes. This is the point. But I is the recurrent class. So this C here. The initial, you can say this is the time n. The I is in the recurrent class, and so this is the one-step integrability from state I to state J, and we claim that this is 0. And so we prove this by what? By condition. Okay. So suppose that Pij is positive, and because I and J are not in the same communication class. So that means that Pgi should be 0 for all n. Why? Because if there exists some n such that this n step changing probability is positive, then I and j must be communicated with each other. Because we already have this for the one step changing probability. Okay, so right. So but then it's impossible for the Markov chain to transit to I once it is in state J. Right? Because if this is it's true, right? But because of that, you have not. So you can see that you assume from I to J this is positive, but from J to I the probability is 0. So you never go back. All right. Now, but I is recurrent, right? If you go out, but you never go back, wow, that means that I is not recurrent. It's impossible, right? So this is impossible. Oh, sorry. All right. So which is a violation to the recurrence of state I? Okay. So that's right. So this must be true. Must not be true. Okay. And so Bij should be 0. Right. So if R is a recurring class, and then you don't have so the transition from a recurrent state cannot go out of the class never. Okay. So that is a property of Markov chain. But it is possible that you can have J to I. It's possible. Okay, it's possible. For example, you can see here. So we have communicating class. There are 2, right? All right, but the 2 and 3 are recurring, but 1 is not recurring. So 1 is transient, and this is recurring. Okay, so it's a recurring class. But from a state not in the recurring class, you can transit to the class, no problem. But 2 and 3 cannot have transition out of the class, right? As stated in the proposition. So. Okay, so now we collect all the transient states together as T, right? And the T may consist of many different transient classes. But for our purpose, we just collect all the transient states together. Okay, they may consist of different computing classes. For example, you may have 4 here and 4 here. 1 and 4. So you have 4 is a communicating class by itself. Okay? So we have 3 communicating class. 1 and 2, 3 and 4. So the set of all transient states is 1 and 4. And so it consists of 2 communicating classes. And now all the recurring class will be identified by itself. So Ri, each Ri is a recurrent class. All right, and so the state space N0 is partitioned into the joint union here. So we have the set of all transient state. We have state in the first recurrent class. We have state in the second recurrent class, etc. Okay. So this is one. And so we can partition the one-state transient equilibrium matrix P, right, by here. Right. So all the state will be listed in here, and all the state in R1 will be listed here, etc. Okay. So we can decompose the one-state transient equilibrium matrix into blocks. Okay, and so the Q is the one-state transient equilibrium from a training state to another training state. Okay, and the L1 is the one-state transient equilibrium from a training state to what? To a recurring state. So it is possible to be positive. Okay, by our study. So all this is possible. But for a state here, if a state is in the first recurrent state, then it's impossible to transit to the state out of the class. So all the zeros here. Okay, so so the one-state transient probabilities from a state in R1 should go to state in R1 too. So you have PR1. So what is PR1? PR1 is itself a transition matrix. Because the low sum of this matrix, this submatrix, will be equal to 1. Okay, so it is already a one-state transient equilibrium matrix itself. Okay, so you can think about if the Markov chain can be reduced only to the recurrent class one, then it becomes to be irreducible. Because we get rid of all the training state, all the recurrent state in the other recurrent classes, and then just leave the state in R1 there. Okay, then this, so we just truncate all the state, right? We truncate all the state, and only to leave the R1 there, then it becomes to a irreducible Markov chain. Okay. And the transient probability, the one-state transient probability matrix will be PR1. Okay, so see, after this arrangement, the one-state transient probability matrix will like here. There are many zero blocks here. Okay, so starting from here, right? There are many, and only a diagonal block. We have a non-zero diagonal block here, and each diagonal entries here. This block matrix actually is a probability, transition one-state transient probability matrix. Okay, so this is the picture we have, and then okay, so when you multiply the p n times, right? You multiply them, you will see that the diagonal term you have n's power, no problem, and qn is also n's power, but there is a part here. It is not the n's power of L1. Actually, it's you have to know is the n-state transient probabilities from a training state to a recurrent state in this class. So the sub n means the n-state transient probability, right? So the L1. So in general, you should take this, but it is not the n's power of L1. Okay, so don't misunderstood. Don't misunderstand the notation. Okay, so here. So you can have a total picture of the one-step changing probabilities as well as the n-step changing probabilities of the market chain. Any questions? Okay, so if I and J are transit states, right? And so it is just you take the ij's entry, right, and the sum over together, right? And this is the same as you sum over the q here, right? You have the q here. So now we focus on q, right? And we let m to be the sum, receive the sum of the power of q, right? Power of q. So so we call this m, and is maybe the entry of mij may be finite or infinite in general, right? Maybe finite or infinite. But we will prove actually the mij by the definition is this summation. Okay, and so that we have Bij zeros, right, and also the n-step changing probability together. So Bij zero is just the delta ij by our definition. And once that, this is the expected number of total visit to state J given initial state VR. And we already computed that before. It's this quantity here. And because J is transient, so if Jj is less than 1, right? The first return probability for a transient state J is less than 1. So the denominator is positive. Okay, so this is a finite number. So we prove that the summation Mij is a finite number. Yeah. Okay, it's a finite number. So this sequence of the series sum of the, or you can say the power series of matrix Q, right? Has a finite sum. So the matrix has finite entries. Remember, the Q matrix may be infinite dimension, right? So it says that we still are able to compute. Okay. So now, if the size of if the number of transit states is finite, then the Q matrix, of course, is a finite matrix. So that the matrix M is finite dimensional, and the M actually is the inverse of this matrix. This is because that we can verify that the I minus Qm, okay, goes to here, and the Qn is equal to 0, 1, because the n-step changing probabilities are equal to 0. We proved that before. Qn, you know Qn, okay, with the n-step, and the limit of Bij and goes to infinity is 0 if the state J is transient. This is from a theorem here. limiting theorem. Okay, for the limiting theorem, we prove that. Because this is infinite, so it's 0. So that this comes to identity. Right? And so if we have two finite matrix that this is identity, then M must be invertible. Okay, this is a basic factor in linear algebra. So that M is just the inverse of I minus Q. So in the same time, we prove that I minus Q is invertible. Okay? Okay, so as we know, Mij is the mean total number of visits to state J in the lifetime given the interstate. So we have that. So Mjj actually is equal to this one, and Mij, because delta Ij is equal to 0, so we have that. So that from these two conditions, then we can reverse to find that we can find the first passage probabilities from state I to state J by using the the mean time, the M entries. And the M entries is very easy to compute because it's easy to find the Q, right? Okay? Once you know the Q, you can find the M by this formula. So you know the Mij, and Mjj. Okay? You know them. And from that, you can compute the Mij. Wow. So that this formula has numerical advantages here. So the Mij can be computed by the Mij. Any questions? Now, and from proposition 4.4.1, we know that if Ij are in different, well, if I is in a recurrent state, but J is out of this recurrent state, then the first basic probability will be 0. You never go out. Okay, so a state in here never go out of the contained class. Right, so this must be 0. Right, and if Ij are in the same recurrent class, then Fij should be 1. So you have done everything, right? Well, if you want to know the first basic probabilities, now you know that you know everything already. Because the first basic probability is very important in the study of multiple chance. So that so for Ij to be, for I and J to be transient states, you already know how to compute it. And if I is in a certain recurrent class and J is an arbitrary class, in arbitrary, right? Then this is 0. And for different, okay. But there is one thing back to. If I is a transient state, but J is in a recurrent state, so what is the first basic probability? We haven't give an expressive formula up to now. So the picture is that so in terms of Fij, then we have T. We have T. This is R1, R2, R1, R2. Okay. So for here, we have already done. So we check it because that for Fij, in the case I and J are training states, so we have formula here. Now, for here, from the state, okay, this all is 0, and this is 1, and this is 0, etc. So for any I and J in R1, then Fij must be 1. Okay, must be 1 here, and this is 0, and 0, 1, etc. But we still don't know this one. Okay, haven't solved yet. Right, so now this is the only case left, right? Remains to solve is that I is transient, but J is in a certain recurrent class. Okay, so that is, and so Fij, the Fij here is that we start with a training state. And then we want to know that we eventually visit the state, recurrent state J. So by the photocopy theorem, we just partition the first state, right? The state at time 1 to M here, and then apply the Markov property that just the Bayesian theorem. All right. So by the Markov property, because the term here, this event is depends only on the future. So we can omit the x0, right? Okay? Because the event is in the future from time 1, so you can forget the history, the time 0. So you have this one. Right. Now, so the M is the state. So you can decompose the state into M in the set of all the training state, and M is in the recurrent state, etc. Okay, so we have that just by partitioning, and so that so we consider all the M in the RT by T not equal to K. Right? Then I should change the order. Right? So M is in RT by T is not equal to K. Yeah. And so this is the I is in the transient state, right? So I is in the transient state, goes to K. So J is in okay, and so if M is in the so let's say, so we consider one by one. First case is that if M is a transient state, right? So so that a transient state, and this is the same as you start with from 0, because this is the transient state, and the first state is the transient state. So it is asked that you start with the transient at time 0, and then to know the first time. So this is the same. Okay, so to be infinite, this is the same event, and this is just the first phase time from a transient state to this recurrent state in RK, right? Do you have any questions about this? Okay, so we have that here, and for M equal to J, because now M is in RK, right? So it's possible for M equal to J. If for M equal to J that S1 is J, and you should the first base is 1 must be 1, okay, because J is a recurrent state. And also, if M is in the same state, this is the same, right? So that you start with a state not equal to J, right? And this is the same as you start with at time 0. You start with the M state in the same recurring class. And this is FMJ. The MJ is equal to 1. So this is also true. And this is 0 if M is in the different recurrent class. So of course this is 0. You never go out. So you never visit the state J. So this is C. Okay, so you know from here. This is 0, so this vanishes. Okay, and this is 1, or 1, right? Or 1, and this is another first phase probability, FMJ. So now you get a system of a linear equation there. So if J is recurrent, and I is the transient state. I is a transient. So the set of all the forces space probability satisfying these system linear equations. Okay, and the PIM and all these terms are known. So you have to solve the system linear equations. So once you solve these system linear equations, you can have all the entries is Fij. Okay, and so now we know how to solve it. So we know the Fij already. Okay. So this is difficult part because you have to solve the system linear equations. But if as we say, if the number of transient states P is finite, then this system has a finite number of unknowns, and just by linear algebra you can solve the system of linear equations. Okay, so and you see that if J, you can see this is system linear equations. All the coefficients does not depend on the state J in the recurrent class, right? For example, if the training state I, you sum over all the m in the recurrent class. So together, this number can be written as beta I RK. Okay? So because it depends on the whole recurrent class RK. Alright? So this part is independent of J. Similarly, the coefficient, right, PIM, right, is also independent of J. So that the system of linear equation is good for any J, right, in RK. So that means that even you have different J, you will get the same set. You will get the same set. That's why we have to find is that they have a common one. So the first page is probability from a state I to any state in the RK will be the same. So that's why the first page will be from a training state 1 to RK, because that we can, for any state J in RK, the F1J will be all the same. So we will establish the system linear equation in this way. It is much more convenient. So we solve the system because they all have the same. So we have Fi R1, we have Fi R2, etc. Okay, so we have. Okay. So basically we complete our study of how to find out the first page probability. Alright, so I have only one section, right, and it is very interesting so I will continue the study of Markov chain next week. Right. And remember, we have meeting that next Tuesday night.